Hi everyone, I'm Yier Lin, and I'm a fourth-year PhD student from Math Department of Columbia University. Today it's a great pleasure to talk about the SPD limits of the higher spin vertex model. This talk is based on two of my papers on arXiv. Feel free to have a look. So we're interested in two SPDEs in this talk. The first one is the Kpc equation, which is given by the following form. So nu and kappa, there are some coefficients, with nu to be positive, and C is the spacetime white noise. The second SPDE is the stochastic telegraph equation, which is given by the following form here, with beta 1 and beta 2 to be some coefficients, and f to be some deterministic function in t and x, which is given, and C is the spacetime white noise. So we're going to look at these two equations on different domains. For the Kpc equation, we're looking at it on the upper half plane, while for the STE, stochastic telegraph equation, we're looking at a quadrant. So you can see actually for these two SPD, they're very different. The first one is of parabolic type, while the second one is a hyperbolic equation. So despite their difference, we're going to show these two SPD arise as the scaling limits of the same model, which is called the higher spin vertex model. So this model was introduced by Cohen and Petrov in 2016. So how is it defined? Imagine we associate the integer lattice in some subset of Z2 with a vertex configuration. So this vertex configuration is specified by four non-negative integers, I1, J1, I2, and J2. So one should understand I1 and J1 as the number of input lines going into the vertex, and I2 and J2 to be the number of output lines going out of the vertex. And we also impose some condition that for the number of lines in the vertical direction, it cannot exceed capital I, and the number of lines in the horizontal direction cannot exceed capital J. We call capital I and J to be the spin parameters. Okay? So they're positive integers. And for such vertex configuration, we're going to assign it with a weight for each of them. So the expression of the weight in general is pretty complicated, in particular when J is greater than 1. So here I only show you the expression when J equal to 1, which is given by the table here. So here, we set this nu to be q to the power of negative I. This was used to ensure that we indeed have at most capital number of I vertical lines. Okay? And for the vertex configuration does not belong to this table, it just have vertex weight to be 0. So our vertex weight will satisfy two properties. The first one is so-called Ice rule, which means for a vertex configuration that have non-zero weight, the number of input always equal to the number of output. For example, if you look at this second configuration, the number of input is 0 plus n, which is n, while the number of output is n minus 1 plus 1, which is also n. Okay. The second property is the stochasticity, which means if you fix the number of input lines, for example here 1 and n, and you sum like all the possible weight, sum the weight for all possible configurations, you will always get 1. For example, you look at this input I and n, you sum these two vertex weight, you will get 1. Then if you assume some positivity of the vertex weight, actually this weight gives you a transition probability from the input to the output. In other words, given the input, you can sample your output according to a vertex weight, which is also a probability measure. This allows you to sample your vertex configuration not just for one vertex, but actually for a number of them. For example, if you look at this square, this 3 by 3 square of vertices, and with the boundary input to be specified from bottom and from the left, then we can do something called the sequential update or sampling rule to sample the vertex configuration for all of these vertices. We start from the vertex on the left bottom. So we have the input, so we can sample the output using the vertex weight. Then for these two vertices, again, we have the input, so we can sample the output like independently. Then again, for the three vertices here, we can do the same thing, and so on. So we can do the update according to this direction. So in particular, we can sample the vertex configuration like on a quadrant, as long as the boundary input is specified. Then after such sampling, like what we get actually finally is a stochastic path ensemble, so formed by like these different vertex configurations, and we can associate it with a height function defined as ntx. So the height function is defined in the following way. Starting from the left bottom corner, we let the height function to be 0. Then as long as we cross the line from left to right or from up to below, the height will increase by 1. And if we go in the opposite direction, the height will decrease by 1. Okay. So at the beginning, we define our height function for the integer lattice, but we can extend it using linear interpolation. So our height function is really a random continuous function. And we can define the same model like on the upper half plane, like, and associate with a height function. Okay. So now we're going to present our result about the scaling limit of this random height function. So just recall that our model depends on 4 parameter alpha q, I, and j, and we set this b to be 1 plus alpha q divided by 1 plus alpha. We first look at the model on the upper half plane, and we tune our q parameter to be 1, okay, while we fix b to be something between 0 and 1, as well as our spin parameters. Then if we apply the parabolic scaling of the height function, we show it converges to the Kpc equation. Okay. So this is the first result. It corresponds to weakly asymmetric scaling for our model. For the second theorem, we look at our model on quadrant. So instead of fixing b as in the first theorem, we let q and b both goes to 1 with certain rate. And we look at the fluctuation field of the exponential transform of this height function. We show it's governed by the stochastic telegraph equation, whose solution is actually given by a Gaussian field. And this weak convergence holds in the space of random spacetime function, random continuous spacetime function. So as a remark, our results actually are the extension for the case of stochastic heat equation, which corresponds to I equal to j equal to 1. In which case, like these results has been obtained by the reference here. Okay. So finally, let us talk something about the proof heuristic. So how to get the SPD limit from microscopic systems? In general, you need to find some discrete SPD, some discrete analog of it. And these discrete equations will usually come from the algebraic or integrable property of our model lying behind. So for example, here we use some property called self-duality of our model, and it tells you if you look at this conditional expectation at time t plus 1, given the information at time t for our height function, is equal to this summation, with transition probability p to be some, so p is the transition probability of some geometric random walk. Then if you look at this exponential transform of the height function with some tilting and recentering, this z will satisfy the following stochastic heat equation, with p tilde is some centering and tilting of the transition probability p here. So now this p tilde really approximates the Laplacian. And m is some martingale. So we want to prove the height function converge to the Kpc equation. It suffices to show the exponential transform of it converge to the stochastic heat equation. Then it really corresponds to a discrete to continuous approximation. So we want to show the discrete SHE converge to its continuum version. I hope this intuitively makes sense, though like for detail, like there's a lot of things to do, which I do not have time to cover. So this is where the Kpc equation comes from. So how about the stochastic telegraph? So if you look at this star, you insert, so you replace x by x plus 1, then you subtract this equation, the same x, times a constant. Then actually you'll find there's a lot of term in this infinite sum will be cancelled out by the property of a geometric random walk, and you just get this simple equality. And this is really a discrete version for the stochastic telegraph equation. Okay? So this is where the STE will arise. Okay? So this is basically everything for the talk. I want to thank you for your attention, and just want to say that I have another recorded talk at the integral probability session about the Lyapunov exponent of the stochastic heat equation with general initial data. Thank you very much.